All right, next I want to talk about the rank nullity theorem in the context of linear transformations over general vector spaces. We've already seen the rank nullity theorem in the context of matrices. So we already know that if I have a matrix A, and if A is an m by n matrix, so that it has m rows and n columns, then the dimension of the row space or the dimension of the column space, remember that those are equal, plus the dimension of the null space has to add up to n. Okay, so we've already seen that. And it turns out that that's actually a special case of the rank nullity theorem applied to the linear operator t, where t of x is ax for some a that's an m by n matrix. Okay, so we know that m by n matrices are exactly the matrices that are going to map Rn to Rm. And this rank nullity theorem is actually a subset of the general rank nullity theorem for this particular linear transformation. So what I want to do is I want to tell you the rank nullity theorem. So rank nullity theorem for linear transformations over general vector spaces. Okay, and so all this theorem says is let t going from v to w be linear, and suppose that v is an n-dimensional vector space. Okay, so it could be Rn, it could be whatever, it could be p sub n minus 1, it could be, if n is 8, then v could be the 4 by 2 matrices, or it could be R8, or it could be the set of at most 7-degree polynomials, just whatever your favorite n-dimensional vector space is, it doesn't matter. So t is linear going from v to w, where v has dimension n. Then it turns out that the rank of t plus the nullity of t has to be n, where what I mean by the rank of t, so the rank of t is going to be the dimension of the image of t, and where the nullity of t is the dimension of the kernel of t. Okay, and so that's the rank nullity theorem. We proved that the kernel is a subspace of t is a subspace of v for general linear transformations. We did not prove that the image of t is a subspace of w, although you can check that that's true. Okay, and you should check that that's true. But it turns out that they are subspaces, therefore they have dimensions. Everything is fine. And so it turns out that the rank of t plus the nullity of t has to add up to n. Okay, so in other words, the dimension of the image plus the dimension of the kernel has to be the dimension of this domain v. Okay, that's the rank nullity theorem for linear transformation.